Good afternoon, everyone. My name is Rakhat Khamitov, and I am very excited to be presenting here our work titled as Incremental Learning of Image Classification Models over Low Data Rate Networks. So this is a joint project between Nazarbayev University and the Tyndall National Institute, and we are presenting it here at the DCOSS. So let's begin with the core challenge that we are addressing in resource-constrained IoT systems, especially in remote environments like agricultural fields. Deep learning models are hard to update, and these models are large and require significant bandwidth, especially if you're talking about image classification models. This becomes a major limitation when the network is low data rate, like LoRa. So our objective here is to enable efficient incremental learning for image classification models in these resource-constrained IoT environments. And then we're going to achieve this by optimizing model transfers to ensure real-time adaptation and minimal data overhead. Our solution is a novel incremental learning framework. The key idea is instead of updating the whole model, we update only the portion of it. And in our case, we only fine tune and transfer the last classifier layer. This is paired with the compression techniques such as quantization and Huffman coding, which dramatically reduces the data size. And all of this is designed to work over low data rate protocol such as LoRa. So here is the core mechanism. We first train the full model externally, say on a GPU cluster, and then this full model is then deployed to the edge. As the new data arrives, we fine-tune only the last classifier and transfer only the last classifier part. This helps us to drastically reduce the data transferred and still gain some performance improvements. For the deployment, we use CNN architectures optimized for microcontroller units, which include MobileNet v2 and the MCUNet family, which were designed by MIT Han Lab. These models are small, efficient, and work well with limited SRAM and flash memory. For example, OpenMV CAM-H7 board, which is equipped with the camera, has following specs: 1 megabyte of SRAM and 2 megabyte of flash memory. For example, and this MCUNet library provides us with tiny models that fit well under these constraints. We run them using TinyEngine, which is an inference engine, which was specifically designed for microcontroller units, which outperforms popular TinyML architectures such as TinyML libraries such as TensorFlow Lite and CMS-ISNN in terms of latency and memory usage. To reduce the transmission size of model updates, we use following two key methods. First is quantization, where we compress 32-bit floats to 8-bit integers. For that, we use affine quantization for precision. Second is Huffman coding, which is a lossless algorithm that further shrinks the data. Both combined reduce the size of the last classifier layer from nearly 1.8 kilobytes to just around 456 bytes. To transfer the models, we developed a custom ad hoc LoRa protocol, which works in two phases. First, advertisement phase, where an edge node, which has a newer model, broadcasts a new model update. And then the second phase is transfer phase, where the update is broken into packets, and the receiver can later request retransmissions if any data is missing. So we have designed this lightweight protocol using using 5 packet types to ensure robust and efficient transfers. We have evaluated our method on a real-world agricultural dataset, which was collected in northern Italy. It includes over approximately 3,900 of insect images, and we only focus on Halimorpha halis, which is a harmful pest. We then split this data to simulate incremental learning. So a small data set, uh, we use only 20%, 25% from the original data set for initial training, the other 50% for fine tuning, and the last 25% for testing. For real-world validation, we used OpenMV H7 board, which is based on STM32 microcontroller. It has 1 megabyte of SRAM and 2 megabytes of flash memory, which is like combined with the LoRa SX 1278 module. And we have evaluated our models with standard image classification metrics such as accuracy, precision, recall, and an F1 score. And the results, with incremental learning, performance consistently improved. For example, with the MCUNet IN2 model, which is shown in this figure, accuracy increased from 82.7% to 88.2%, and the F1 score from 81.3% to 87.6%. And this shows that even small update to the last classifier layer gives us significant performance boost. You might ask, what's the trade-off for all this compression? Well, in our tests, quantization had a very minimal impact on performance. For example, in case of MobileNet v2, accuracy and F1 scores stayed almost the same. And for other types of models, there is a negligible drop in terms of performance. But this is a price that we pay for a 4 times size reduction. And for the MCONet IN0 model, the metrics, performance metrics, stayed the same even after the quantization. So let's quantify the savings. So to store the last classifier layer in FP32, we would utilize 1.8 kilobytes. And after applying quantization, this number reduces to 456 bytes. After applying half-moon coding, the size reduces to approximately 384 bytes, and this is almost a 5 times a total reduction, which is absolutely essential for working with low data rate networks, especially if we are talking about LoRa protocol. We have tested runtime on device. The fastest model was MCUNet IN0 with an inference time at 43.7 milliseconds and only 50 kilobytes of SRAM usage. The MCUNet IN2 model had the highest inference time, but nonetheless, all of the models fit comfortably within the device constraints of 1 megabyte of SRAM and 2 megabyte of flash memory. We have tested this runtime. We have tested this inference on approximately 700 images on our OpenMV H7 CAM board. And with this, we confirm that real-time inference is feasible. Finally, we have tested the model transfers over LoRa. So what we found is that even the largest update of 456 bytes took only 5.7 seconds to transfer on average at a spreading factor 7. Smaller models transferred in as little as 3.2 seconds. And in the experiments, all transfers had success rates higher than 90%, which well within LoRa's duty cycle limits. To summarize, we have introduced a lightweight incremental learning framework, which is optimized for resource-constrained IoT when we have low data rate networks. So the key idea was separating the feature extractor from the last classifier layer and to transfer only the last classifier layer parameters. So by using quantization and Huffman coding, we reduced update size to under 500 bytes. And this system delivers performance improvements and adaptability and works well within LoRa's limitation. So for future work, we want to explore other ways of updating parts of the model, not just only the last classifier layer, as maybe by updating the more deeper layers of the deep learning models, we might gain more performance boost. We also would like to evaluate multi-device network scenarios, especially with request collisions, retransmissions, and more complex duty cycle rules. And this is it for my presentation. Thank you for your attention, and goodbye.